Hello, calculus students. This lecture will be on a method of anti-differentiation that uses what's called a basic substitution. Now, by way of review, complete the summary of indefinite integrals below. First thing you'll notice is that every integral is in terms of u, as indicated by all of these differentials. So we think of u as the independent variable. First integral, we have u to a power, and this power n is a constant. We use the power rule for anti-differentiation, and we get u raised to the n plus 1, and then divide by that new power, and then plus our constant of integration. Now, of course, this formula breaks down if n is negative 1, because we can't divide by 0. So we must assume that n is not negative 1. Otherwise, for every other choice of n, this formula works. So that begs the question, what happens if I integrate u to the negative 1? Well, this is an integral of 1 over u du. In either way it's presented, the result here, as we discussed in a previous lesson, is the natural log of the absolute value of u. If we have the nth root of u to the n, then convert this to a power, this would be an n over m exponent on u, and then of course we just use the reverse power rule. So we would add 1 to that fraction, and then divide by that new power. The integral of e to the u du is just itself, and more generally, if b is a positive constant, but not 1, then the integral of b to the u will be b to the u divided by natural log of that base. This is a more general situation of a constant to the independent variable, whereas this is a very specific case where the base is e. This formula could be applied in this case. So you would need to divide by the natural log of e, but the natural log of e is 1, so the integral of e to the u is just itself. This next column are all reversals of trig derivatives. The integral of sine, if we begin with cosine, just check with differentiation, the derivative of cosine is negative sine, so the integral of sine needs to be negative cosine, plus our constant. The integral of cosine is positive sine, check with differentiation, derivative of sine is cosine. Integral of secant squared is tangent of u. Integral of cosecant squared is cotangent of u, but we'll need a negative here because the derivative of cotangent is negative cosecant squared. Integral of secant tangent will be secant. Integral of cosecant cotangent will be negative cosecant of u. Next column, we learned earlier the derivatives of all the hyperbolic trig functions, but for integration we'll just emphasize integrating hyperbolic sine and hyperbolic cosine. And differentiating either of these functions goes back and forth without producing negatives. So the integral of hyperbolic sine is just hyperbolic cosine, and the integral of hyperbolic cosine is hyperbolic sine. No negatives to think about here. And the last two on this page are reversals of some of our inverse trig, emphasizing just two of them. The integral of 1 over 1 plus u squared du gives us our arctangent of u, or you can write that as tan to the minus 1 of u, or inverse tangent. And our last integral of 1 over square root of 1 minus u squared du gives us the arcsine of u, or you could write that as inverse sine of u. All right, let's go to the next page. Find the indicated derivative, then use a basic substitution method to find the indicated antiderivative. First, a review of a derivative. In general, if you have the sine of some function u, and you do a derivative with respect to x, then we must use the chain rule. We'll get cosine of that same argument, and then multiply by the derivative of the argument, which I'll put in the front. So when I differentiate sine of 4x squared plus 1, I will get cosine of 4x squared plus 1, and now multiply by the derivative of 4x squared plus 1, which will be 8x, and I'll put that in the front. So notice that there's an x to the 1 here in the front of this cosine, and an x squared involved in its argument. This is a natural consequence of a chain rule having occurred. Imagine if this had been a 3 power instead, then I would expect to see an x squared in front. Of course, this 8 would be different. If this was an 11 power, I would expect to see a 10 power on this x, of course with a different coefficient here. Let's put this back to square. Okay, next what we're going to do is this integral. Well, notice how similar that looks to this derivative over here. The only difference is that we have an 8 coefficient here, but a 3 coefficient here. In particular, if I were to suspect that a chain rule has occurred, and I differentiate 4x squared plus 1, I would get 8x. What matters is that I get a multiple of x to the 1. And notice I see an x to the 1 here in front. So it does have the appearance of a chain rule has occurred. And now I want to reverse that chain rule. What we're going to do is called a basic substitution. Now, there are multiple ways to go about doing a substitution, but I want to share with you 7 steps that consistently work, provided the integral is possible via a substitution. Step 1 is assign a substitution u equals f of x. Now what we're going to do is we're going to call some component of our integrand u. And if you look at our derivative rule in orange here, I'm going to call the argument of the trig function u. So this portion of our integrand, we will convert to u. Let u be equal to 4x squared plus 1. And then to investigate the effects of the chain rule, I do need to know what the derivative of this u is. So I'll use Leibniz notation du dx. This is the derivative of u with respect to x, and we would get 8x using the power rule. This was step 2. Step 3 is solve for dx. So we're going to treat this like we would a normal fraction, where I can multiply the denominator to the other side. So that gives me du is equal to 8x dx, and then divide both sides by 8x. So dx will be equal to du divided by 8x. And now I want to substitute into my integral. Well, I've already highlighted orange, what I'm calling u. I also want to substitute on this differential, dx, and convert it to du over 8x. And now we will work on step 5. We're going to convert to an integral with only the new variable u. And that includes the differential needs to go from dx to du. So this integral can be changed into 3x times a cosine of, and my argument becomes u, and there's multiplication here, and the dx becomes du over 8x. Now, if we've done a good substitution, we should be able to eliminate all of the original variable through cancellation somehow. And because we have multiplication here, I can imagine this 8x being underneath the integrand instead. That would allow me to do some cancellation. The x and the x will cancel. Furthermore, we have a 3 divided by 8, so my new constant coefficient will become 3/8, and I can factor it out of the integral. This becomes a brand new integral in terms of u, where because the differential is now du, I can think of u as the independent variable and anti-differentiate. And the integral of cosine is sine. So we get 3/8 sine of u, and now is a good time to put your constant of integration. And we've now done step 6. Notice that when you integrate, the integral sign and the differential disappear at the same time, that we replace the cosine with its antiderivative, and this is also the step in which you need a plus c to show up. And now we have the final step, substitute back to the original variable x. So this u right here, we will convert it back to 4x squared plus 1. This is called a back substitution, and we do this only after you've anti-differentiated. Make sure you don't back substitute for this u prior to anti-differentiation. And so we get a final result of 3/8 of the sine of 4x squared plus 1, and then plus our constant. Now, when you're considering doing a substitution, some common choices are to let u be an exponent on a constant base, or to let u be a denominator, or to let u be the base of a power, or relatedly, let u be a radicand, which is what's inside of a radical, and recall a radical can be converted to a power, or to let u be an argument of a trig or hyperbolic trig function. And this was the case for our first example here. We let u be equal to the argument of the cosine in our integrand. Now we'll practice these 7 steps on the next slide, but on this page I want to show you a slightly different way you might go about doing the substitution. So I'll rewrite the integral. I'll still do these first 3 steps. So u will be 4x squared plus 1. So du dx is 8x, and in the same step I'm just going to put this dx over here. I still want to do substitutions, but I'm going to take a slightly different approach. What I want to do is I want to construct this statement in my integrand. Well, notice the x is already present, and so is the dx, but I need an 8. Currently, I have a 3. So I'm going to do the following. Factor this 3, which I don't need, to the front. I'll rewrite the rest, and now I'm going to insert the number I do want, which is an 8. However, I can't just multiply this by 8, I change it, unless I also divide by 8. In other words, this red 8 over 8 is just 1, so I'm multiplying the integrand by 1, but then splitting the 8s up. When I do this, these 3 highlighted portions, 8x times dx, can be converted to simply du. So we get a 3/8 coefficient times a cosine, and I'll call the argument u again, and then the orange highlighted portions, 8x dx, simply become du. And notice I get to an integral that's no different than this integral. It was just a slightly different manner to go about the substitution. I refer to this as constructing the du. So this presents an alternative way to go about a substitution. As we go through problems, I may go back and forth between using these 7 steps exactly as they're laid out, or using this method I'm calling of constructing the du. Of course, we would then continue the problem and in the end get the same result here. Okay, next page. 3 examples on this page. All will require a substitution. Here we have some choices about what I might call u. Recall on the previous page a list of some common choices. So in this case, I see we have a radicand and we have a denominator. So let's consider both options. I could let u be the radicand, or I could let u be a denominator. In this case, only one of these will be helpful. If I let u equal the denominator, then the derivative of u, in this case with respect to z, would just be 5. I'm not seeing how this is going to help me cope with the complication of this natural log expression inside of a square root. So instead, I'm going to let u be equal to the radicand, and that's what's inside the radical, but not including the radical. And the derivative of u with respect to z will just be 1 over z. And I'll put the dz over on this side right away. I do see this being helpful because I see the dz and a division by z, which is exactly the orientation I have for this du. So I could just construct the du rather easily here, but I'll go ahead and use the 7-step approach. So the next thing I would do here is solve for dz by multiplying this z over to this side. So dz can be rewritten as z times du. And now I'll do two substitutions. The radicand will be converted to u, and the differential dz will be converted to z times du, and make only those two changes. So this becomes an integral of the square root of u. We have division by a 5z, and then our dz becomes a z du. And sure enough, we do see cancellation of the z's, and that 5 in the denominator can be factored to the front as a 1/5. Square root of u can be converted to u to the 1/2. And now I have a very basic integral that I can use the reverse power rule on. So integration comes next. Add 1 to 1/2, we get 3/2, and then divide by 3/2. This is the time where the plus c shows up, and also the integral and du disappear at the same time. Instead of dividing by 3/2, multiply by 2/3, and multiply it to this 1/5. So 1/5 times 2/3 will be 2/15, and we have u to the 3/2. And now I'll do the back substitution. The u is converted back to natural log of z plus 1, and that's being raised to the 3/2. And if you want, you can convert the power back to a radical notation. The 3/2 power means we're doing the square root of the natural log of z plus 1, and that's being cubed. And we are done. I leave it to you to confirm that if you differentiate this, and don't forget you would need to use the chain rule, that the end result would be the original integrand. Next case. We have a rather complicated looking expression here, and also notice that u is already the independent variable. So when I do a substitution, I don't want to use u again, I just need to use a different letter instead of u. I'll go with w. Now some options on a substitution, looking back at our list of common choices, because we have e raised to the something, I think I might let my new variable be the exponent on this e. So this 3 tangent u, I'm going to call a new letter, and we'll use w. So w will be equal to 3 tangent of u. Let's find the derivative of w next, would be 3 secant squared of u, and then times du. Notice that we have a secant squared here in the front, matching this secant squared. This is a good indication that we are on the right track. This time I'm going to take the construct the dw approach, because I already have a secant squared times a du here and here. What I don't have lined up is we have a 3 here, but a 7 here. So I'm going to factor that 7 out, and in its place I'll put a 3, and I'll counter that 3 by dividing by 3. And then we have the secant squared of u, we have the e raised to the, and I'll change this to w now, and we have a du. And now I have constructed my new differential, dw. All of this combined with that du will make a dw that I'll put at the end. So we have 7/3 the integral of e to the w dw. Now we must do anti-differentiation next. And the integral of e to the w dw is just itself. This is arguably the easiest case of anti-differentiation. And now that we've anti-differentiated, I can do the back substitution. So we get a final result of 7/3 e to the, and then w was 3 tangent of u, and then plus c. I leave it to you to verify that if you differentiate this function, you will get the original integrand. Okay, this last case, I see we have a base to a constant power. So my first thought is to let u equal that base, e to the t plus 11. Let's find the derivative next. Du will be equal to just e to the t, and then I'll multiply this dt over there in the same step. So we already have the du constructed. There's an e to the t and a dt, and that's all we need to make the du. So I get to rewrite the integral. The 2 in the front stays. There's no need to manipulate the constant in this case. The base of this power is just going to be u. So we have u to the 5th now. And then the green highlighted portions just become my new differential du. And now we can just use the reverse power rule. The 2 stays. The integral of u to the 5th is u to the 6th over 6. And then we'll add our constant. The 2 over 6 becomes a 1/3. And then I'll do my back substitution. Change u back to e to the t plus 11. And that's being raised to the 6th. And we are done. This time I will show the confirmation. So the derivative with respect to t of this function. So we're going to use the generalized power rule. The 6 will multiply to the 1/3, giving us a 2. The base gets rewritten. The power drops from 6 to 5. And then the chain rule, we multiply by the derivative of the inside, which is just e to the t. And so you could rewrite this derivative as 2e to the t times e to the t plus 11 all raised to the 5th, which perfectly matches our original integrand. Okay, let's move on. Find the indicated antiderivatives. First one is an integral of tangent. On our summary of antiderivatives on the first page, you might have noticed that we did not have formulas for the integral of tangent or cotangent. We're going to explore how to find these antiderivatives now using a basic substitution. In the case of tangent, I'm going to rewrite it using a trig identity. It's equal to sine of t divided by cosine of t. Now, one option for a choice of u, scrolling back, was to let u be an entire denominator. Let's take this approach here. So we'll let u be that cosine of t. So the derivative of u with respect to t is negative sine of t. And I'll move the dt over right now. Well, we almost have the du already constructed. I just need a negative on this sign, which I can counter by multiplying by another negative, which I'll put in the front. So negative of a negative just goes back to positive. So I've not changed my integral. So I now have constructed the du. We need a negative sine t dt, which I now have. And of course, the denominator will become a u. So rewriting our integral, the red negative in the front stays. Everything highlighted in green just becomes du, and our denominator becomes just u. Now this du you can pull off to the side and write this as 1 over u du. And I recognize now we have a natural log antiderivative. So we get negative natural log absolute value of u, and plus our constant, and then our back substitution. Now this is commonly memorized as the antiderivative of tangent, but there's another version of this answer that's also acceptable. Now recall this property of logs that if you have a log b, that you can bring that a up as a power on that b. So this negative 1 I can bring up as a power on that cosine. This is not the same meaning as putting the power negative 1 right there. This is one complication with this notation. This means arc cosine. This notation with the power outside the parentheses means do 1 over cosine of t, which is secant of t. So I could write my answer as the natural log of absolute value of secant of t. Either one of these is correct. And I've seen both used in different textbooks by different authors, by different mathematicians. It doesn't really matter which one you use. Okay, you can imagine something similar is going to happen for cotangent. We're going to rewrite cotangent as cosine of w over sine of w, dw. We're going to let u be the denominator. The derivative of u, so the derivative of sine of w is cosine of w, and then I'll multiply the dw over. And this time we don't need any negatives. The cosine w dw is already constructed here. And we just need to change the denominator to a u. So I get du over u. The antiderivative of this will be natural log of absolute u. And then the back substitution, this will give us natural log of absolute sine w plus c. And we are done. Okay, now we have two more on this page that look very similar. They're just reciprocals of each other. Despite them being so similar in appearance, they will require completely different methods to integrate. Let's do the one on the right first. When you have multiple terms in a numerator, but a single term in a denominator, recall that when you add two fractions with the same denominator, you can combine this into one fraction with that common denominator. I'm going to do this property backwards. So I'll rewrite the integral as x over x plus 1 over x. And this is convenient because this simplifies to 1 plus 1 over x. And now I don't even need a substitution to finish this. The integral of 1 with respect to x is x, and the integral of 1 over x is natural log of absolute value of x. And we are done with this problem. Now, in this other case, though, we have a single term in the numerator and multiple terms in a denominator. Be careful, you cannot do the same thing. You cannot split a numerator up in the same way you can split a denominator. So we need a different approach. I will use a substitution, and I'll let u be the denominator again. Well, the derivative of u with respect to x is just 1 in this case. And now I'll multiply the dx to the other side. So this is telling us that du and dx are interchangeable in this case. So if I rewrite the problem, the numerator is x, the denominator has been converted to u, and the dx we can just convert to du. Notice this time, though, we have an x still that does not cancel with any other x. Be careful we do not treat it like a constant. I cannot factor the x out and then integrate the 1 over u. I have to find some way to completely convert the new integral entirely into a function of only u. There can be no x's left if I'm to proceed. Well, the key to doing this will be to take my u equals x plus 1 and solve it for x. So x must be equal to u minus 1. this gives me the key to substitute on that x. So I can do one more substitution. X becomes u minus 1. This is over a u, and we have a du. This puts me in a position where I now have two terms in the numerator, but a single term in the denominator, so I can use an approach like we just saw over here. I can split a denominator. So doing so, we get u over u, which is 1, minus 1 over u, du. And now I integrate in terms of u. And the integral of 1 is just u, and the integral of 1 over u is natural log of absolute u. And now I do back substitution. Each u becomes an x plus 1. And we are done. And I do want to point out another way you could write this answer. Recall that this plus c represents all possible constants. And then we have a free-floating plus 1. All free-floating constants can be absorbed into the plus c. So I could leave my answer the way it is, or I can simplify it to simply x minus natural log of x plus 1, and then plus all possible constants. This is often done just so we have a simpler looking antiderivative to look at. Of course, if you had stopped here, this is also a correct answer. Now, the fact that I had to use this substitution not once, but twice in order to convert all x's to u's, I personally refer to this as substitution with a twist. Just a cute way of saying to use your substitution twice in a clever way in order to convert the original independent variable entirely into the new independent variable u. All right, next page. Find each derivative and antiderivative. Okay, we'll do this row by row. The derivative of e to the 3x, using the chain rule, is e to the 3x times the derivative of 3x, which is just 3. Sometimes you don't need to use a substitution to reverse a derivative. You just need to be able to think of the derivative backwards. So when I want to integrate e to the 3x instead, I know I'm going to get e to the 3x with some potential different coefficient plus a c. And the question is, what should I put right here so that I have a correct antiderivative? Well, if you differentiate e to the 3x to test this, that derivative would produce a 3 in the front, but we don't have a 3 in the front here. So we need to put a coefficient so that the 3 that's produced by the chain rule will cancel. And that coefficient is 1/3. Now, you could actually formally use a substitution, let u equal 3x, and then do a basic substitution. This will confirm that you get 1/3 e to the 3x plus c as a final result. But here I'm trying to illustrate that you don't always need to go through the formal motions of a substitution to understand how to do an antiderivative when the chain rule produces a constant. Let's go to the next one. The derivative of the sine of 8x. Well, the derivative of sine is cosine. The 8x would stay the same. And then the chain rule would say now we have to differentiate 8x and put that 8 right there. Well, now I want to do this backwards. I want to integrate cosine of 8x. Well, I know I'm going to get a sine of 8x because the derivative of sine produces cosine. But once again, the question is, should I put a coefficient here so that this is a correct antiderivative? When I differentiate sine 8x, I do get cosine 8x, but times an 8. But there's no 8 here. So I need to put a 1/8 in front of this so that the 8 that gets produced by the chain rule will cancel with the 1/8. And now I have a correct antiderivative of cosine 8x. Now it's possible to get this result by doing a formal basic substitution. You could let u equal this 8x and then go through the motions of a substitution, and you'll confirm this answer. Third example here, if I differentiate the tangent of 4x plus 1, the derivative of tangent is secant squared of the same argument, and then chain rule times the derivative of 4x plus 1, which is a 4. So if I want to integrate secant squared of 4x plus 1, well, I know the integral of secant squared will be tangent of the same argument. So I want to put something right here that will counter the chain rule. And as you can guess, I'll need a 1/4. So when I differentiate tangent of 4x squared plus 1, I do get 4 secant squared of the same argument, but then times this 1/4, and that'll convert it to just secant squared, and then plus c. Okay, fourth example. Here I'll need a generalized power rule because I have a function raised to a constant power. So that says the 7 will drop down, the base will stay the same, and the new power becomes 6, and then the chain rule has us multiply by a -2, which is the derivative of the base. Well, now I want to anti-differentiate 5 minus 2x just to the 6th, which matches this part here. Well, the derivative of the inside is a constant, so I can simply do a reverse power rule and a reverse chain rule in my head. So I know that we'll have the same base, the power needs to increase to 7, and then I need to put in here a coefficient so that this 7 and this -2 will cancel. That means I need to have a 1/7 and a 1 over -2, which multiply to be -1/14 as a coefficient. Well, if we test it, the -1/14 would just stay, If you differentiate 5 minus 2x to the 7, you get this result. But then when you multiply this by negative 1/14, that's just like dividing by negative 14. And you can see why, in the end, all the constants will cancel, giving us a result of just 5 minus 2x raised to the 6th. Now, these last two, you could have done formal substitutions. In this case, let u be 4x plus 1 and then go through the motions of a substitution. And in this case, we would have let u equal 5 minus 2x and then gone through the motions of a substitution. Now, what's consistent about all of these is that if you had done the formal substitution, notice all our choices of u have derivatives that are just constant. So note that if the chain rule results in multiplication by a constant, then anti-differentiation will involve division by that constant. This is a pattern we are seeing in these 4 examples. Okay, and then the last page. Here we're going to do a definite integral, but for a function that will require substitution in order to integrate. Now this integrand is x over x squared plus 3. The graph of it is shown over here. We are integrating from negative 1 to 4, so from here to here, which means we're going to get a net relative area as an answer. This region that's below has a negative area, and the region above has a positive area. You can tell from the visual that the positive area occupies greater space than the negative area, and so when I combine these relative areas, I'm still going to have a positive result. We'll say A1 represents the magnitude of this area, and A2 represents the magnitude of this area. So the meaning of this definite integral will be area 1 minus area 2. Now keep in mind that these limits of integration always match the differential. So they are both x coordinates. If I want to use the fundamental theorem, I need to find the antiderivative of this function. Notice that the derivative of x squared plus 3 involves an x, which I see right here. So I do see that I can construct a du if I were to use a substitution on the denominator, which is what I'm going to do. We'll let u equal the denominator. Then the derivative of u will be 2x times our dx. I'll take the construction approach. I want a 2 in front of this x, so I need to counter it with a 1/2. And now I have 2x dx. I can make a du out of that. And of course, our denominator will just become u. So in my next line, I would write the integral. We have the 1/2 in front. I'll pull the du to the side, so we have a 1 over u and then the du. And the question is, what limits should I put here? If I keep this negative 1 and 4, then you have to be careful. Because if you look at this integral out of context, the default assumption would be that these numbers are u coordinates in order to match the differential. But they are not u coordinates, they are x coordinates. So to get around the default assumption, we need to write that these are in fact x coordinates, not u coordinates. And now we continue. So we have a 1/2. The antiderivative of 1 over u is natural log of absolute value of u. We don't need the plus c for a definite integral. We can just choose c to be 0. And then we're going to evaluate from negative 1 to 4. But again, these are x coordinates, not u coordinates. So be careful that you don't just plug 4 in for u, because it's not a u coordinate. In other words, just make sure you do the back substitution next. So we have 1/2 natural log of absolute, and the u becomes x squared plus 3 again. And now this we can evaluate from negative 1 to 4 safely. So we plug in 4 first for x. That's 4 squared, which is 16, plus 3 is 19. An absolute value of 19 is just 19. So I don't need to keep the absolute value bar. Minus, and then 1/2, and now plug in negative 1. Negative 1 squared is 1, add 3 is 4, and absolute 4 is 4. So we just get natural log of 4. And we are done. This is a good answer. But I could do a little bit of log manipulation. I could factor out the 1/2. Then recall the property that if you subtract 2 logs, you can divide their arguments. So I could write my answer this way. And then I can move that 1/2 as a power on the argument using another log property. And a 1/2 power means a square root. So I get square root of 19 over square root of 4, which is just 2. So here's another way to write your answer. And all of them are acceptable. My personal favorite here is either this one or this one. But they're all equal to each other. Okay, now another way around this issue is when I do the conversion to a new variable u, I can also convert the limits that are x limits to new limits that are u limits. In other words, I can take this substitution and say, when x is the lower limit negative 1, this means that u will be equal to what value? You plug negative 1 into the substitution. Negative 1 squared is 1, add 3 is 4. And when x is 4, plug that into our u substitution. 4 squared is 16, add 3 is 19. So u would be 19. Which means from here, we can also change the limits of integration. So I have a 1/2, and the lower limit becomes a u coordinate of 4, and the upper limit becomes a u coordinate of 19. Now the default assumption is that whatever number here should be this coordinate, a u-coordinate, and whatever number here should be also a u-coordinate. And since they are, I don't need to bother writing or specifying that these are u-coordinates. I can just leave that off because that's the default assumption anyway. Okay, so from here, we get the 1/2 natural log of absolute value of u. We don't need the c, but we evaluate from 4 to 19. We don't need to do a back substitution in this case because I converted the coordinates to u-coordinates. So I can just plug in 19 now, in for u, and that gives me a natural log of 19, and then minus and plug in a 4 for u, and I'll get a natural log of 4. From here, we get all the same results. So when doing a definite integral involving a function that required a substitution to do the antiderivative, you have a few options. Keep the limits the original coordinate, just make sure you specify that every time you write them, or do a conversion to new limits based on what the new variable is, in which case you never have to do a back substitution. You just complete the problem, but in terms of u. All right, this concludes our lesson on basic substitutions.